just now, this morning, figured that I had to post, I posted them to there's actually an ELC page for this course seminar. This guy actually created a course. So that's one place, and I think I can even just randomly add people to that, but I haven't figured out how to do stuff like post it on YouTube. Once upon a time I knew how to do things like that. So for the moment, that'll be where they are, which means if you're not actually registered for this, but you can, so that's where they'll be, and if you want, I'll send an email about that. That's how you can access that. But there's probably a better solution. Maybe they can be made public, I'm not sure. Someone can tell me later. Okay, so now I'm recording. And now I will share. And, okay, so this is my report on my investigations of I0 diff plus of F4, which we don't know much about that group. There is a paper by Bulut that, if it's correct, claims that it's not, shows one non-trivial element in it, but there's some question about whether, I don't know, I haven't looked at it carefully. And so if we have pi0 homeomorphisms, that's trivial by the Alexander trick. This paper is about trying to like relate it to some other groups and also give some explicit generators for at least a kind of geometrically meaningful subgroup of it. That's what this talk is about. So just very quickly, I had a kind of diagram where I'll say it a little bit differently. I was talking about, let me get some more space here. So I was trying to talk about, at one point, at one place in the thing, I had pi1 of, I had S infinity last time, but maybe that was overkill, kind of confusing the point. Sn is the space of embeddings of a disjoint union of n two spheres into a connected sum of n S2 cross S2s, punctured. We have a little picture to go with that, sort of the schematic for connect sum of S. I draw S1, S2 cross S2 as if it's S1 cross S1. So this kind of looks like there's my puncture over there. So this would be a picture of 3 S2 cross S2s. I don't know if my colors are the same as last time, but you kind of think of the meridians as being, so that the red will be the base point, which is the sort of standard embedding as S2 cross point. There's sort of natural collection of, so that would be 3 two spheres there. If I do these 3 two spheres, those are some dual ones that I want to keep track of. That's not the base point in this space. And then I also maybe just mentioned some parallel spheres, draw them in pink. Maybe I should make that a little bigger since I can afford to. Anyway, this is just, so this is a loop of embeddings. So I've got all 3 of these red two spheres moving around and coming back to that standard position. That's what I'm dealing with. I described a map. Well, I haven't described, I described a little bit a map to pi0 of diff plus of S4. This is the most sort of geometrically natural thing here. And I'm going to put a little surjection with sign with infinity over it. And what that means is this map, which we call HN, H for handles, you're attaching, you're thinking of the N two spheres as being handle attaching maps. If you let N get large enough, if you're trying to hit any particular element of pi0 diff plus of S4, for large enough N, you can hit it. And you can describe that as giving a map from a limit of groups, pi1 of S infinity. But we don't need to be that fancy. Then this just contains naturally the kernel of that map of HN. I described, there's also a sort of pi1 of S and 0, which maps to here. It might not be the whole kernel. I don't want to put that 0 there. And so what this is maps, this is loops of spheres that stay transverse to the blue stuff, to the blue sphere. And so the red sphere, the base point is transverse to the spheres. If you stay transverse for all time, then you're going to cancel. That's the rough idea, and that's why you're in the kernel. Then there's another pi1 of Sn hat. So Sn hat, there's a map there. Call that map I star. So this is ones that, these are embeddings which stay disjoint from the pink stuff. So a parallel copy of the base point disjoint of spheres. And that's just, so that's a sort of, kind of seems sort of complementary in some sense. Then inside here, I've just got the image of the composition, Hn, well, I'll write infinity. Yeah, Hn composed of I star. So this just naturally maps onto there. So this then, one content is that I can describe. I'm going to put equals infinity, equals with an infinity sign, which means that when you take a limit, I can get the full thing here. A subgroup, a group of mapping classes generated by certain, well, they're indexed by the ends, and I'll tell you what those mean. So what this is saying is, here's a certain subgroup of the mapping class group of S4, and I can give explicit generator. Here's a certain subgroup, and then as you let n, there's a limit as you let n go to infinity, and the limit of all of those, which is just the union of all of those, is equal to, is generated by certain explicit things that I will describe. And I'm going to start by trying to describe those explicit things.
Dave,
yes.
when you talk about transverse to blue, do you mean dual in some sense, or do you just mean like
Well,
intersecting transversely or disjoint or?
Well, I mean, right. So, well, notice that these are loops starting and ending at the base point. The base point transversely intersects at once. So staying transverse actually means through all time, you're geometrically dual.
Okay, thanks.
Yeah. And so, as I was trying to emphasize, a big question here would be, if I look at these, put these two together, this and this, they both map into pi1 of Sn, and I want to know, do these generate together? Generate. Do these generate this? In other words, can every loop in Sn be expressed as a concatenation of loops? First that stay transverse to the red, and then that stay disjoint from the pink and back and forth. I'm sort of agnostic on that, but if that was true, then that would actually tell you that this was an equality here. So that would be an equality, and then I would have an explicit set of generators for the whole mapping class group. Okay, so now I want to try to, since I want to try to get to the more explicit four-dimensional geometry here, so I want to describe these. And so first of all, what are W of I? W of I are the embedded objects that describe these diffeomorphisms, tau, and the tau stands for twist. You're supposed to think of it as kind of like a Dane twist. So W of I is a Montesinos twin, and there's going to be one for each integer and each natural number. I'll tell you what those ones are specifically. What is a Montesinos twin? In general, I use the notation W is a pair R comma S, where R and S are oriented. For me, its orientation is important. Two spheres in S4 intersecting transversely twice. So I'm going to tell you how for any Montesinos twin, there's a natural self-diffeomorphism, isotopy class of self-diffeomorphisms of S4, and then I'll describe a particular set of Montesinos, a particular list of Montesinos twins that I care about. Okay, so what's the picture? So the first claim is that given a pair of oriented two spheres intersecting transversely twice, the given W equals this pair R comma S, the neighborhood, so the boundary of a neighborhood of R union S is diffeomorphic to a 3 torus. And I'll write it there, and then it sort of factors in a natural way. I'll write it S1L cross S1R cross S1S. I think that's Montesinos' original notation. So L stands for longitude, R stands for R, S stands for S. So I'll draw a picture that makes this a little clearer, but let me, first of all, this is, this factor is characterized by the fact that this S1 cross point are homologically trivial, sorry, in the complement. So that L stands for, hence longitude. This stands for the fact that R, this is a meridian to R. In other words, it bounds a disk that transversely intersects R once. And this factor is a meridian to S. And I claim that when R and S are actually oriented, then there's a canonical, this up to isotopy, and this parameterization is well defined with its orientations. So just a quick picture to, I think I won't do a full justification of this fact, but sort of lower dimensional, if I sort of draw two S1s in any two manifold. Let's suppose this is R and this is S. And then I take a regular neighborhood of that and take a boundary of that regular neighborhood. You'll notice that a boundary of the regular neighborhood of it, in an oriented manifold at least, is 4 circles. So what's 4 circles? 4 circles is S1, so half-dimensional. Well, here what you're seeing is S1 cross S0 cross S0. So the picture is, so where's the, so this direction, this is the longitudinal direction. This is your S1 longitude. And then
Did we just lose Dave?
Yeah.
Yes.
Guess his internet went out like mine. I couldn't cook up on time because my internet was glitching. We're in the same neighborhood, so who knows what's going on here. The question is, has he noticed? I'm gonna text him.
think I'm back.
Okay.
Hopefully you were all saying wise things while I was gone. I think it was just straight up computer failure. Can you see my screen again?
Yes.
Yeah. At least I didn't see you saying anything or drawing the green thing.
Okay. So this was, okay, so I'll back up a little bit. This was a schematic, a mix of dimensions, sort of like at face value, like literally it's just two S1s in S2, I guess, and a boundary of a two-bit neighborhood of that configuration as S1 cross S0 sub R cross an S0 sub S. But then I was saying you can sort of imagine a little bit better if you are willing to mix dimensions. You can imagine the, you can try to imagine the actual full S1s. This is a S1S, which could just as well be over there, and then maybe in a different color. This is your S1 sub R. I think in the interest of time, I'll ask you to sort of believe that this is a natural thing. It's, I don't know, are there any questions about this? Besides, I mean, I claim you can figure out why it's true with some work, and it's not that hard.
So there's a,
Go ahead.
Okay. That's important, I think. Oh, my question is just, so it has nothing to do with the sign of the local intersection?
Well, yeah, so one intersection will be positive and one will be negative. I mean, because I'm in the four sphere, right? Because these have trivial normal bundle and so forth. They have to be they have to have opposite signs. And it's certainly not true if you have arbitrary two spheres of arbitrary self-intersection, arbitrary form endpoints. Is that kind of what your question was?
Yes. Yeah.
Then, okay, anything else?
so there's a simple case, which I guess is pretty trivial when the two intersection points are very close together. Or in other words, you take two tangent, two spheres, and then move one of them a little bit.
That's right. And that's even if one of the two spheres is knotted, that could be an interesting case. I haven't really thought of it. In my case, I'm always going to deal with a situation where one of them is unknotted. Actually, so another good prototype example, that's a good prototype example to have in mind. Another good prototype example to have in mind is what you get when you spin a knot. So if the normal, not spinning a knot in 4 dimensions means you take a knotted arc in 3 dimensions with its endpoints in a half plane with its endpoints in a half space with its endpoints on the half plane. And then so here's a half plane. If you think of the half plane as a 2 sphere and you spin this knot around, then that knot spins out another 2 sphere, ST sub k, and these two spheres intersect transversely at 1 point, 2 points. So a good prototype example is this. And I think Montesinos in some sense was interested originally in generalizing this setup. Any other questions? So then from this is you get that therefore the neighborhood of a boundary of the neighborhood of R union S will then be, -1, 1, take the outward normal first convention, S1L cross S1R cross S1 sub S. And then there's a very natural self-diffeomorphism of this manifold, which is where you take a Dane twist here. So that's an annulus cross the identity cross the identity. And that's what I'm going to call the twist defined by defined by the twin W, by the pair of 2 spheres. And it's only well defined up to isotopy, but I claim it is well defined up to isotopy by the given data. In fact, by the isotopy class of the twin. Are there any questions? Okay, so now,
Sorry, it's an irrelevant question. So this Montello hair.
Montesinos?
Yeah, so it works for any spheres that intersect one positive and one negative in any four manifolds?
If they also are self-intersection 0,
Okay, I see.
then it's correct. Because it's really another way to, one way you can find this out is just find any explicit model of a plumbing of two trivial disk bundles over S2 plumbed at 2 points with opposite intersection.
Okay. Yeah. Thanks.
Yep. Okay. So that's what the tau sub W is, which will be a well-defined element of pi 0 of diff plus of S4. Now I'll tell you, I'm going to describe some very explicit. I'm going to tell you what WI is for I, a natural number. Actually, I'll just draw a picture of W of 3.
Should Dave,
yeah.
what should I think about of this longitude? It's like the two arcs, one connecting the intersection points in one S and the just that's like
yes.
sort of the Whitney disk boundary.
Yes, so that's exactly right. I mean, right, so that you can think of the two intersection points as being north and south pole of both spheres, right? So you go, it's a push off. I mean, on the spheres, you can go, one arc from north to south pole of one sphere and then back up to the other sphere, right?
Mm-hmm.
And then you push that off to the into the bound of the neighborhood.
Mm-hmm.
But you have to be careful about twisting, so that so when you do that, you have choices of how many meridional twists you can pick up as you go around, and you want to do it in a way that it becomes homologically trivial in the complement. So this may also be, maybe I didn't quite answer Weiwei's question correctly. In an arbitrary 4 manifold, there may not be a well-defined longitude, because there may not be homologically trivial in the complement.
So you need this SL to be homologically trivial in the complement.
Yeah, I mean, it will still be true that it's diffeomorphic to a 3 torus, and you'll still have well-defined. The second two, these factors will be well-defined, but this factor will only be defined up to, possibly adding multiples of the other, the two meridional twists in the other direction. So I'm not sure what happens whether you have. I'm not sure that you can argue how well defined this Dane twist will be in general. I have to think about that more. But the point is, this S1 sub L factor, this factorization of a 3 torus into a product of 3 circles is part of the information needed to get that, is knowing that the S1 sub L factor is homologically trivial. Okay. Okay, so now I'm going to draw a picture in the next page of a specific Montesinos twin. I have fun drawing this picture, so I'm going to draw. So I think of this as this is like a snake eating its tail. So here comes I'm going to explain this picture after I draw, or maybe it's like a snake with its tail going through its head. So that's the head of this. This is the snake. Just put 2 eyes and a tongue for fun. That's the head of the snake, and here's the tail coming and piercing through its head. I'll explain that a little bit better soon. Then the tail's going to come up. Then I'm going to come all the way around. So I'm drawing a sphere, right? So I'll go around one more time. The number of times you go around is precisely the integer I that I care about. So currently in R3, I've drawn a single 2-sphere intersecting itself transversely along 2 circles. but we want to think of this happening in R4. So I'm going to shade a little bit of it red and shade a little bit of it blue. I mean, blue and red. What I mean by this is that here the usual thing where you have two sheets intersecting in R3, and if I want to resolve that intersection so that it becomes just an embedded thing, I can push one of the sheets up or down in the fourth coordinate. And so blue and red is up or down in one of the other coordinates. So I push the little bit of the snake's head, that little annulus, either up in one direction and down in the other. So that now it's an embedded two-sphere. So that's like an over-under thing. I claim it's actually still unknotted as it is, but now I'm going to put the second two-sphere in. Are there any questions about this picture of a two-sphere?
Yeah. So the head, so you're going under and then over and you're coming out on top of the head?
Yeah.
I see.
Like it goes in one ear hole and out the other ear. And then I'm going to take the other, so that's going to be, let's say, R. Maybe this is R of 3. And the other one is going to be the same for whatever the eye is. I'll draw it in the green or something. It's going to look like this. Let me. So it's going to look like a ring. So I'm drawing what I see in three dimensions. And so the 2 points of intersection, this picture is kind of bad, but if you imagine it, so it's piercing the tail. So it's like a ring that pierced the tail. And so it intersects the surface of the snake in 2 points, one on the top and one on the bottom. And that's a ring, but then in forwards and backwards in time, so in the fourth coordinate, x4, you cone off in both directions, plus or minus one direction. So in other words, that's going to be a standard that's a slice of a two-sphere when you go, this is all happening at x4 equals 0. When you go to x4 a little bit positive, everything black, almost everything black disappears, and then you can shrink the green circle to a point, and same thing in the negative direction. And then this is the sphere S. Are there any questions about that?
So if somebody gives this to you, how do you compute the 3?
Oh, I guess it's it's a very explicit, it's the number of intersections there. How about that? I mean, yeah, you could argue, is it 3 or is it 2, but it turns out that this is 3, the way I've drawn it. I'm just giving you a very particular drawing. And that's 3, and I would have 4 if I go around 4 times. And
So both components are unknotted?
both components are unknotted, yes.
So what you drawn is 2 S2s and they intersect in
2 points, which are right here. The other one you can't, my picture doesn't give justice. There's one on the top of because when it pierces through the tail, right? It goes in once and then out the other point.
I see. So there are 2 points in there. Yeah, okay.
Okay. So W.
Are they not like parallel in S4 or something? I mean, how complicated can 2 unknotted two-spheres intersecting in 2 points in S4 be?
I think interesting. Well, it's not obvious that the twists along W, if you go 4 times or 5 times. I'm not sure. That's a good question. But if you could show these were all these. I mean, so when you if you don't twist at all, you just get a sort of the standard unknotted pair, which would be like the spin of an unknotted arc. But I don't know. That's a good question. But I have reason to believe. I mean, I don't. An interesting thing is that I claim there's an isotopy exchanging these two. So in fact, R of I, comma S as a pair is isotopic to S, comma R of I. interest. And in fact, actually, that sort of brings up a point. So,
and you're probably working like with isotopies through pairs of spheres intersecting in 2 points.
yes, absolutely, yeah. So, by the way, this fact here. So an interesting fact is that if you do the twist along some Montesinos twin RS as an isotope, at least up to isotopy, that's the inverse of that is the twist along the Montesinos pair. I'll call it W bar, which is SR. So if you just switch the two components, I don't think you switch the no, just don't switch the orientation, just switch the two components. I claim that will give you the twist and the opposite twist. And so the consequence of this is that in the subgroup, so tau's consequence of all of this is that, let me get this right. Yeah, so that means that twist along W of I squared is the identity. Because if you switch two factors, it's isotopic to the same thing. And actually, Gabay and Budney have another way to see this same diffeomorphism, and they can also kind of, in a very similar kind of like moving stuff around and seeing that you can switch two factors of something, seeing that this element is the identity. So a consequence of that is that everything in this there's this subgroup that I'm interested in that may be all of the mapping class group. It's the subgroup generated by these guys. Therefore, everything is order at most 2. Oh, something I often say when I first start talking about this that I forgot to say is that the smooth mapping class group of the 4 sphere is abelian. And that's an interesting fact. It's just because the 4 sphere can be made is built out of 2 4-balls, and you can have the 2 4-balls have space between them. So you can make if you have 2 self-diffeomorphisms of the 4 sphere, you can make one be the identity in a ball, and you can make other one be the identity of a ball, but you can make the place where one of them is the identity be the place where the other one does stuff, and then they're only doing things in disjoint balls. That's a slightly more complicated argument than that, but that's the basic idea. So it's abelian. Therefore, this subgroup is generated by things of order 2, and it's abelian, so everything in it has to be order of most 2. And so I don't know. That's just for whatever. So it may be that if you can show that this is the entire smooth mapping class group, then you show this fact about that. Or you could disprove this fact by finding something of higher order.
So Dave, I have a question. I mean, naive question about the picture above. Maybe, so just to make myself more, understand this picture a little bit more.
Yeah.
So what happened if my, the snake's head, back off?
Okay, so you want to think that's like this red and blue stuff. It's like an over under. So it's a little bit like this in lowered in. It's a little bit like this in not exactly.
So that is embedded, right? So this sphere is embedded.
The sphere is embedded, but my projection into 3 dimensions is immersed.
Right. I think I understand this point. So what I'm wondering is that if my snake head back off,
yeah,
then gradually this kind of immersion in the projection will disappear.
Well, okay, so the red and the blue will get closer and closer to each other, right?
Yeah, but one is already positive in the 4th coordinate, and the other is negative. So
That's
although they get closer and closer, so they only get into non-immerse in the projection. But even if you get across this blue and red, they seem to still preserve, remain being embedded in 4 dimensions. Is it true?
Well, I mean, look at the knot over there. If you try and, I mean, just what he wrote in 3 dimensions, right? So try and pull that. You're going to have one place where they intersect one time.
Yeah, but we're in 4th dimension, and this blue and red are kind of, you know, you have the 4th coordinate that.
No, but we have you have extra dimension, so that.
Yeah, I think you're still stuck. I mean, yeah.
Okay, yeah, maybe.
This 3-dimensional picture is not a perfect analog, but
that's exactly my intuition is not helping me at all.
yeah.
So it's the picture of the clasp in the lower dimension. That's like the picture if you like grabbed the tail on either side of the head and tried to pull it out the top of the snake's head. Like that doesn't work. But what you could do is if the green sphere wasn't there, you could pull the snake's tail out of the mouth by grabbing like to the right of the snake's head and just pulling that way, right? It would like slide out.
Right, that's right. You could pull, yeah, if there's no green circle, the tail can move up
Right.
and come out of the ear holes, right? But moving the head to the right is not going to work. Okay. By the way, I mean, you know, what Jeff was asking, how complicated can this be? You know, an interesting question. It's conceivable someone can just show on the nose explicitly that all these diffeomorphisms are trivial. These twists along these particular W of I's, and then that would be interesting because it would show that the subgroup of identified is actually trivial and maybe the whole mapping class group, but I'm not sure. Again, I don't see how to do that. You know, it's hard to like do explicit isotopies. One of the things you should always bear in mind if you think, I'm going to just start to move stuff around and show you that something is trivial, is that, you know, in dimension 2, for example, if you want to prove some relation in the mapping class group, you always end up coming back down to a disk and saying, well, for the 2 disk, the mapping class group of the 2 disk is trivial. But this is sort of the fun. We don't even know if the mapping class group of the 4-ball RAL boundary is trivial. So it's going to be, if you want to make explicit arguments, they've got to be really explicit. You can't just push all the problems into a 4-ball. Okay. Let me just give a couple other questions here. So one question is, well, I can make a little claim that I won't prove. I want to get to trying to give some idea why this is true. So a little claim I won't prove is that if, you know, given any Montesinos twin, if S is one, if one component is unknotted, then actually the twist is in this. The twist along W is in this group. So it can be expressed as a composition of twists along these special Montesinos twins. I don't know an explicit proof. I just know that you can turn it into a sort of theory problem and explain it that way. But the bigger question is, you know, what about other Montesinos twins? Where neither component is unknotted. And then more generally, you know, an interesting way, kind of how I first got into this, thinking about this was, you know, given any embedding of a 3 torus into S4, you get a twist, right? You get a twist along that 3 torus. I mean, you have to have it parameterized 3 torus, and then you twist along. You take a neighborhood of the 3 torus, -1, 1, cross the first factor, do a Dane twist there across the identity, and that gives a map from S4 to S4. And you can ask, that's an interesting subgroup, I guess, of an interesting collection of elements in pi0 diff plus of S4. And you know, you can ask, are these all isotopic to Montesinos twin twists? are they in the other group? And then it just becomes interesting to think about what are some interesting embeddings of the 3 torus into the 4 sphere. And at first, way back, I had no idea of any interesting ones, but a lot of them come from the Montesinos twist, but there are twins, but there are much more than that.
Yeah,
Okay.
so Dave, I
Yeah.
mean, like the obvious candidate is just knotted 2 tori in 4 space. Is it? Are
Okay, for a
Montesinos
knotted
points
2
more
torus,
general than that?
yeah, the boundary of a knotted 2 torus, well, it depends on which factors you're going to look at. I think I convinced myself that most of those are not going to give interesting examples. If I think maybe if any of the 3 factors bounds a disk everywhere, so it'll if the 3 torus bounds a 2 torus cross disk, then I'm pretty sure you're going to get an isotopic to the identity. I mean, there are 3 different ways in which you could bound 2 torus cross disk, but I think any of them will give you something isotopic to the identity. Actually, I'm not quite prepared to. These are questions to get conversation started, and I've forgotten a little bit about what I did or didn't know about these questions. Okay, so some ideas for proof. So there are 2 parts of the proof, right? There's, let me just pause, save in case I lose my work, scroll back up and look at what I'm trying to do. This picture. So one thing is prove the surjectivity, and then another thing is prove the equality to of this particular the things coming from this subgroup, and show how they come from, why they come from these Montesinos twins. So maybe, so both, I'll try to sketch both kind of quickly. So so first of all, surjectivity of H infinity, so you're just given you're given some diffeomorphism of the 4 sphere. Step 1 is this cool fact that phi is pseudo-isotopic to the identity. So that's already a huge machine. What pseudo-isotopic means is that there exists a diffeomorphism, capital Phi, from 0, 1 cross S4 to 0, 1 cross S4, taking such that 0 cross S4, phi restricted to 0 cross S4 is equal to the identity, 0 cross the identity, and phi restricted to 1 cross S4 is equal to the given map little phi. And if phi was restricted, if phi maps T cross S4 to T cross S4, it would be a regular isotopy. But here it can mix up the levels, and then you don't know. And the reason, I won't write it down, but the reason every diffeomorphism of S4, what did I say, of S4, diff plus of S4. The reason every diffeomorphism of S4 is pseudo-isotopic to the identity is precisely because there are no exotic 5 spheres. So you build interesting 5 spheres by gluing 5 balls together along diffeomorphisms of S4. And I mean, there's probably a direct argument that follows the same line, but if you believe that people have already shown that, then that's all you have. So then the next part is to say, well, what can I do with this pseudo-isotopy? I'm going to try to use the pseudo-isotopy to understand the diffeomorphism. And so I try to capture the information about the diffeomorphism by, we say, okay, consider F0 from 0, 1 cross, we consider a Morse function on 0, 1 cross S4 to 0, 1, which is just going to be projection onto the first factor. And then I'll take F1, which is the pullback of that by this pseudo-isotopy, P0. So that's F0 composed with E. So that's notice that both of these are Morse functions with no critical points. And then you try to construct some homotopy, F sub T, for T between 0 and 1 from 0, 1 cross S4. So some 1 parameter family of Morse functions with maybe births and deaths and so forth happening in the middle. And if f sub t has no critical points for all t, then that implies that capital phi is isotopic to an isotopy. And so this is all Cerf's idea. And he used this in higher dimensions to show, that pseudoisotopies are isotopic to isotopies in various cases. And by showing how to remove critical points, you have a one parameter family starting with a Morse function with no critical points, ending with one with no critical points. In the middle, interesting things happen. So then you refer to Hatcher-Wagner, who studied Cerf's work a little more carefully, and you find a lemma that says you can always get a Cerf graphic, in this case, to look like, this is called the Cerf graphic when this is the value of the function, f sub t, and this is t. And you plot the critical values, the sets of points where the derivative is not surjective, and you can always get it to have some picture like this, where it's a bunch of nested i's. And what this means is, and I'm going to draw it, these are all, remember, this is 0, 1 cross S4 is the manifold. It's a 5 manifold where the Morse function is being studied. So what will happen is you'll have, as time increases, you'll have a birth of a canceling pair of 2, 3 critical points, and then more 2, 3 critical points, and so on, all the way to, so there's lots of content here. The fact that you can only look at index 2 and index 3 critical points, the fact that there's no crossings in the Cerf graphic, and so on. Very, very quickly, there's quite a bit of work to be done here, including using Gabai's light bulb trick. But from what you want to think in the end is that, where were these connect sums of S1 cross S2s? So if you look, the idea is that, maybe my picture is a little too small, but let me use a different color here. The idea is that to the left and the right of these blue lines, you can sort of make everything standard. So you just have, standard births and standard deaths of canceling pairs of critical points. And then the interesting stuff happens here. And what happens there, really, you look across a middle line there, and what you see there, because you've started with, so the way to think about this is, over this point is a 4-sphere. And then you've attached a bunch of 5-dimensional, 4-sphere cross I with 5-dimensional 2 handles. You can arrange that nothing interesting is really happening down here either. And those 2 handles don't move, and everything interesting happens in the 3 handles. So after you attach some 2 handles, trivial 2 handles in a non-interesting way to S4, this 4-manifold becomes a connect sum of n copies of S2 cross S2. So that's why we land in this manifold. And then the 3 handles that are attached are precisely the, they're a 5-dimensional 3 handles attached along a 2-sphere. There are n of them. They start in a canceling position, run around somewhere, and come back to a canceling position. And so all the data up here that characterizes everything is contained in the data is basically your pi1 of your space of embeddings of spheres. That's the, super fast outline. There's lots of, basically the hard work is making all the arguments about things being standard in the blue regions. And it's not going to be given to you as standard, and you have to do some work. But I want to then quickly, and so that the idea is that captures everything that's given by this loop. And furthermore, you need to argue that then that loop actually determines the isotopy class of you want to think of sort of along here, you want to think of this being phi, and here you want to think of this being the identity. And so phi up to isotopy becomes determined by this loop of spheres. So I won't pause for questions because I'm just plowing ahead, and I want to say, how the connection with the Montesinos twins. So then, once you have it in this Cerf graphic in this nice picture, of index 2 and 3 critical points, there's a handle trading operation, which I could tell you more about if I had time, but I don't, which it's basically a surgery of a certain kind. These are all index 2 and 3, which switches them to be 5-dimensional index 1 and 2 critical points, canceling pairs. And this trading operation, this is where I made my first mistake 6 months ago or so. This requires that, if you remember, requires that you're in pi 1 of Sn hat. That was the loops of spheres that remain disjoint from a parallel copy. And that's what I didn't understand, but I don't have time to explain. And then once you get into this situation where you're, so now what you want to think is that I've got a 1-parameter family of Morse functions on S4 cross I, and somewhere in the middle, what I've done is I got S4, and then I attach 5-dimensional 1 handles. Those are attached along pairs of points, and then 5-dimensional 2 handles, which start out canceling, move around, and do something interesting, and end up canceling. And now, from here, you do an argument that you can, because having gotten down to index 1 and 2, there's a lot more flexibility in how you can move things around. And in particular, all these births, all these eyes can be made disjoint. So from a surf graphic point of view, you can more or less, you can basically pull things out. You can pull each of these eyes out one after another, so that it looks like this. And then you can, there's an operation where you, if there's a death, then there's a birth. And so you can get it down to a single 1-2 pair. And finally, this means that what you've got in this mid-level here, so you again kind of have a standard outside some boxes, and everything is determined by something happening here, and that 4-manifold there is now, when you take S4 cross I and attach a 5-dimensional 1 handle, you get a connected sum of, well, you don't have a connected sum because there's only one of them. You just get an S1 cross S3. And then the 2 handle is attached along a circle. So everything becomes governed by an element of pi 1 of the embeddings of S1 into S1 cross S3, rather than the embeddings of lots of S2s into lots of S2 cross S2s. So that's the extra work there. And then this was studied and explicitly understood by Budney and Gabay. They gave explicit generators for this. And then the final work is saying, okay, I've got this circle moving around in S1 cross S3, and then I do surgery on it. Let me understand what happens to how that, what that does to S4. And then we get this, you think carefully about what happens if you push a circle around and come back to the start and then do surgery and to get back to S4, and you realize that really you've done one of these Montesinos twists. So, and so Budney and Gabay's give explicit generate loops of S1s and S1 cross S3s, and when you do surgery, you turn those into Montesinos twins. So I've got to stop, and that was too fast at the end, but maybe it gave you some idea of what happened. So, questions, thoughts?
Let's clap first.
Oh, thank you. I think, does Zoom do something where if like lots of people are clapping at the same time, you can't really, they cut each other out, because it tries to prevent there being lots of noise at the same time.
Maybe, yeah.
Yeah. Okay, so questions?
Hi, Dave. May I ask some questions?
Yes, please.
So, well, maybe I'm missing something, but to the end, you need to show that these elements are not smoothly isotopy to the identity, right? There has to be some detection result here.
Wait, oh, I never said anything is non-trivial, if that's what you're talking, if that's what your question is.
Oh, I see.
This entire content of this, these theorems could be all theorems. All these theorems are true if all the groups are trivial, right?
Oh, I see. Okay, I see. This is, I see. Okay, this is a generating result. So
Right. So
I see.
I would love it, someone else or me, to show that these groups are non-trivial. So then I actually know that what I'm saying is something useful. Or you could try to use this as a technique to show that the big group is. I mean, if I could show, you know, I have this subgroup of the diffeomorphism group, the mapping class group, which might be, I showed how if you could do something about loops of spheres being generated by these two subgroups, then I could show that this this group generated by this Montesinos twins is the whole smooth mapping class group. And then if you can explicitly show that each of those twists along Montesinos twins is trivial, then you would have the theorem that the smooth mapping class group of S4 is trivial, which would also be a big deal.
I see. That makes sense. Okay,
But also finding invariance would be amazing.
I see.
But Dave, you said if a certain thing is true, then you actually can generate a whole mapping class group. Then
Yeah.
but then you still don't know whether it's non-trivial or not.
That's right. That's what I was saying. So over here in this picture, I was saying if the images of these two subgroups, these two loops generate all of this, then I would know that this group generated by Montesinos twins was equal to the whole diffeomorphism group. And then, like I said, still everything could be trivial. All groups could be trivial, but this could be a strategy to actually prove that the smooth mapping class group is trivial, if it is.
Mm-hmm.
Because now you have explicit generators. If you could show each of those is trivial, then you're done.
But then your your twins can be just, so you can just pick one of these kind of twin spheres.
Yeah.
And this fixed pair can already generate the whole thing. If what?
No, actually, so the twist along W of 1 and the twist along W of 2 and the twist along W of 3 are not obviously related to each other. This is more like this is like a Z to the well, actually it's a Z2. This part ends up being a Z2 to the infinity, a Z2 to the infinity. Each one of these generators is order 2, and then there's a countable list of them.
But like this suggests that any Montesinos, if this was onto, then any Montesinos twist would generate everything for any pair? Is that what you're...
No. This is not, this suggests that so if this was onto, then any Montesinos twin would be expressed as a composition of twists along these particular Montesinos twins.
I see.
But it doesn't mean that any Montesinos twin would give you everything. In fact, it would mean that the twist along every Montesinos twin is order 2. And if this is really a Z2 to the infinity, then it would not generate everything.
I see.
Yeah.
Question.
Yeah.
In the 2-3 like critical point in the surf graphic,
Yeah.
How is it easy to see that you can push the attaching sphere off of the canceling two-handle belt sphere?
You mean like to get something interesting happening in here?
Yeah.
okay, what's hard to see is examples, right? Because, you know, when you start with a two, you know, even just a single two handle and then a canceling three handle. So that means the two handle is attached along a circle in a four manifold, and then the canceling three handles attached along a two sphere, which, you know, which intersects the belt two sphere. So you get two spheres intersecting transversely once, right above that. And then I'm not saying you can always move this off. I'm just saying there may be interesting loops of where one, you know, the belt sphere for the two handle stays where it's fixed, and the attaching sphere for the three handle starts moving around. And if it remains geometrically transverse to the belt sphere for the two handle, then it will cancel for all time. And you could clean up the surf graphic and make all the critical points go away. The interesting situation is where that's why you had that kernel SM0. The interesting situation is where it starts developing more and more complicated intersections with that belt sphere. So then it stops looking like a canceling one. And then after going all over the place, it comes back to just being a simple canceling two sphere, three handle. So, I mean, visualizing that is highly non-trivial, and that's something Hannah Schwartz and Dave Gabay and I have been messing around with for a long time. Hey, let me end. How about I end with a question that I always want to throw. It's like related, but I can never figure out how to put it in talk properly. I won't even write it down. So there's the Schoenflies problem, which the smooth Schoenflies problem, which says that every three sphere embedded in the four sphere smoothly embedded in the four sphere bounds a smooth four ball in the four sphere on one side or the other, or on both sides. It's a consequence. Something I've never seen anybody talk about that's somehow related to this is, I like to think of it as the slice.
You're writing something because it's
okay, I'll write it down. I was gonna not. So here's a question. I'll call it the slice Schoenflies problem. Informally speaking, this is easier than the Schoenflies problem, although I don't know how you would actually do it. Does every three sphere, everything is smooth here, embedded in the four sphere, bound a four ball embedded in the five ball? The real Schoenflies problems would ask you to embed not in the five ball, but in the four sphere itself. So it doesn't appear to be related at all to what I said. I don't have time to tell you why, but I asked a couple, you know, older people who thought about the Schoenflies problem over the years, and they were like, I don't know. It's kind of weird. It's like sort of an obvious, you know, if you're going to study the real Schoenflies problem, this is sort of obviously could be easier. So why not start there? But as far as I can tell, no one's really thought about it. John? All right, I'm gonna stop sharing so I can see your faces. Stop sharing. Why is it not working? Why is stop sharing not working?
You stopped sharing.
I did. Yeah, you know, this happened to me before. I stopped sharing, but your faces have all disappeared. And
you have to click on the top somewhere where it says.
Yeah, no, I did that. Do you see me still?
But I see I was trying to click something else, and I guess I unseed myself.
So, yeah, okay, here we go. No. This is like a super annoying thing that happens to me with some regularity. And if I do this, and then see here.
Did you click on gallery view up on
No,
top?
I don't even have, it's like it looks like I'm not even, it's really really weird because I know I am, but it doesn't. I'm gonna go out and come back in, and I'm gonna leave the meeting. I'll make Gordona the.
There he comes.
I'm back. I don't know. It's really weird. You guys hear me? I can't hear anybody now.
We can hear
Oh,
you.
yep. Good. Yeah. Great. Okay. Good. We're good. All
Can
right.
you see the gallery now?
Yeah, I'm good. Everything's normal. So next week is Joan Licata, and then I think Kyle, you're after that. Does that sound right? And then at some point we have Jeff and Alex are going to speak, and then Akram's going to talk later, November.
Good.
Cool. I was passing by Ted's Most Best and thinking, you know, they're we should go there sometime. And we could go in small, you know, small batches of topologists or something.
Yeah.
Anyway,
It's very far away from
Yeah.
each other.
everything seems far away when you're just spending all your time at home.
Does anybody know what the situation with numbers is in Athens right now? I mean, suddenly after this huge number, and after being getting, you know, 3 sick people per week in my classes, I suddenly have 0, and everybody suddenly has 0 sick people. So it becomes suspicious to me.
Yeah, well, I mean, I think it's clear that, I mean, it's clear that people realize there's nothing in it for yourself to report
Right.
positive, right? I mean, even, you know, when I was talking to people back at Max Planck, they were like, you know, having even Germany, like the contact tracing app, you know, it just means, Sashka was saying, if you have the contact tracing app, all you learn is that your friends aren't reporting COVID positive. So I don't know. I don't know those numbers, but I mean, I think the actual, like, you know, hospital numbers are you know, I don't know what to make of the UGA numbers, but Athens numbers are probably a little more, you know, reliable, even though they don't come out that frequently. And they do seem to be going down, and to the point where the schools are, you know, looking at the numbers and wondering whether they're going to start K through 2nd back in public school. I would trust those.
You know, because like it's the question of how big is the contagion in the community, whether it's safe to go eating, whether one feels safe to go eat in a restaurant or not.
No, I understand. Yeah, I don't know how you know that. It'd be nice to have some real data, but I have no idea.
Anyway, my husband is such high risk that I don't.
No,
say anything.
Yep. Cool. All right. Well, I should have stopped recording a while ago.